Can someone give me a if you can hear me? Hey, Sandra, how are you today? Thank you, Luis.
I'm good. How are you?
Good. Awesome. On. Still a little bit of record keeping, and that's significant digits. We have to go through the a review of significant digits, and then we can move on to Newton's laws. So let's get to it. Well, I'm going to review the basic rules of SIG-DIG, and then we'll look at uncertainty and talk about how you can determine. So, once you know what significant digits are, then there's certain rules of using them to manipulate, algebraically, and how significant carries through without and under the context of algebraic manipulation, which ultimately points to or is determined by the uncertainty of measurements, which we can then define. But I'm guessing to some degree, again, these things you have obviously been introduced to on some level. So let's just make sure we're all on the same page as we move forward. So, rule one. The leftmost non-zero digit is the most significant number. So examples of that, a couple here. So The number is 107, 107.0, 00107. So some of these numbers, I'm just kind of exaggerating them in the way that we wouldn't necessarily write them that way, but I'm just doing it so that it emphasizes the point that I'm making the property. Yeah. So I have a series of examples that I've written here in different ways. Same numbers. Well, yeah, same. Well, and they're not all the same number, but same digits, but written various ways. And obviously, this is the simplest rule: the leftmost non-zero significant period, no matter whether you have decimals or non-decimals, is the most significant number in that in these examples. And so let's also do something here. So we'll do something like the most significant number, the least significant number, and the total number of significant digits in the number. So in these examples, the value 1 in all of them is the most significant because it's the leftmost. All right. Yeah. Second rule, in the absence of a decimal, the rightmost non-zero digit is the least significant. So again, the number is 107, 1070. Well, actually, I guess I could just choose these. Yeah. Same values here. So, well, yeah, I'll just do it again. Yeah, so in these examples, the value 7, so the rightmost non-zero digit is the least significant. So in this case, obviously that 7 is that value. In this case, there is another digit beyond, the 7, but it is 0. So the rightmost non-zero digit is the least, which means that the zero is not significant. And again, even though in this number there are digits to the left, they are to the left as opposed to the right. So anyway, all those examples are the case. Yeah. I guess I have to write this thing over and over again if I do that. So yeah, again, in these numbers then, yeah, I don't know any other way to do this as opposed to writing it over and over again, please. And total. So here we have the value 1 is the most significant, and 7 is the least significant in all of these. Yeah. Yeah, I guess what happens with that. All right, third rule. When a decimal is present, the rightmost digit is the least significant. Okay. So here are some examples of that. 107 and 0, 107.03, 107.01. And even though this is technically something that could be written, it's not something that you would normally see, but again, just for the purpose of illustration. So most, least, and total. Guess we can start to do that now. So in this particular rule, well, so a decimal is present in all of these numbers, and the rightmost digit is the least significant. So in this case, the 0 is significant. So you can compare 107.0 as compared to 107.0. Since the decimal is present now, then it is the 0, the rightmost digit, that's the least significant. In this number, the 3 is the least significant. The 1 here, and in this case, yeah, so I guess it would be this as well. That's 0. So the least significant, the value then is going to be, just to complete this through, is 0, 3, 1, and 0. Now, this rule doesn't incorporate any, just whether it's a decimal or not, it doesn't matter. It's just period. The left, that's the easiest rule. It doesn't matter what it is. The leftmost digit is the most significant. So if you were to compare that to these numbers, in this case, the 1 is the most still, this guy. So then the total number of significant digits now can be determined by these combination of these three rules. So in this case, I've got a total of 4 significant digits. This case, a total of 5. Again, 5. And here also 5, between the most and the least. Again, here the most significant digit, as we said, is the 1. So then the total number here, we can now also determine. And in most of these, all of these are going to be 3. So 3 total significant digits between the most and the least, 3 here. And again, most significant non-zero digit to the left, that's the rule. So again, the total number of significant digits here is 3. And now also this guy we can do as well. All right, everything. So the least. Now, I guess I kind of mixed the numbers here. So least here, in this case, this is the least, because there's a decimal there. Decimal here, well, it doesn't matter, but here, so least, because that's a non-zero digit. So the total number and least, if we complete this chart, we got 7, 0, 7, and 7. And the total number here then, between the most and the least, 3, 3, 4, because of the decimal, and then 3. And the final rule, well, that's what I just was showing you here, is that every number between the most significant and the least significant is also significant inclusive. All right. Any questions about that? Any surprises? All right. Let's make a few calculations to illustrate how significance carries through. Oh, right. Sorry. Before that, let's determine how to just review how to determine significance in the first place. When you're making a measurement, that is, from using a device like a meter stick or whatever. So when you're making a measurement, let's use a meter stick as a basic example. There's a general rule that the least the something called the least count determines how significant you can make, how significant of a measurement you can make with a particular device. The rule of thumb that I use is that you can always determine a measurement to one digit beyond the significance of the least count. The least count is the smallest unit of measure on the device. So on a meter stick, the least count is the millimeter position or the tenths of a centimeter position. Right? It's the smallest increment of measurement. So let's take a look at that. Least count, kind of an old school term, but I don't see it used much anymore, but it's how I was taught, and I like it. So the least count, the smallest unit of measure on any measuring device. So that's when you're pick up a measuring device, that's the first thing to determine. The smallest increment of measurement. On the device. All right. One can always determine one significant digit beyond that of the least count for a device. Generally. Generally, a measurement can be made to one significant digit, abbreviating here on SIGDIG, beyond that of the least count. This digit is the estimated value of the measurement. and essentially determines the uncertainty. Okay. Uh, okay, let's look at a quick example, illustration, I guess I should say. There's any of those will do. Sorry, talking to myself. Yeah, so let's just take an example of a meter stick. And maybe it looks something like this. Yeah, so just like if I have something like this, uh, hopefully you can see that pretty well. So this is 10 and 11. And then I have a block that's doing something like, let me blow it up, make it a little bit bigger. So let's say that this is a block of wood and I'm making a measurement. And so we just cut off the other ends over here. All right, so again, these represent centimeters. This is a millimeter, right? And let's make this measurement in centimeters. So obviously, the block is at least 10 centimeters and 4 millimeters. So that's going to be 10.4, right? But here, as I said, the least count is the tenth of a centimeter's position, the millimeter, which means by the rules I've stated here, we can actually go one digit beyond that, and it's the estimated value. So again, my eyes can't really see that well without aid, without using a cell phone or something to blow it up. It used to be, but most people, when I was young, I could pretty much tell whether or not an object fell right on any of the hash marks or if it were in between. I'll give an example of in between in a minute. Now, right now, it doesn't look like it's in between. So I would then estimate that the measurement is exactly 10.4. And so the estimated digit would just be a 0. But because I can go one digit beyond that, I need to put that, because based on the rules that I just erased from the 4 rules of significant digits, that because I can place a decimal there, because I can obviously see that it's 10.4 and I should place a decimal there. Then if I don't put that, it implies that the number is only significant to 3 significant digits, and that's not true. When I put that estimated value, now because the decimal is there, it makes this number more significant. This value here becomes determines ultimately the uncertainty to what degree of significance you can make a measurement with this device. So therefore, for any device, the least count actually determines, that's what I mean, it determines how significant the digit is, and also tells you what value in that for that device is the uncertain value. So so this digit would be significant to 4 digits. It would have 4, the total number of significant digits in this case would be 4, because you're placing the 0. And the most insignificant value is going to be 0, which determines the uncertainty of this, this. And I know I haven't really defined uncertainty. You probably have an idea or maybe even know what it is. But, like if I had a vernier caliper or a micrometer, I could make a measurement of this object to more significant digits, and based on these same rules that I've determined. So the uncertainty really kind of tells you how significant you can make, how precise a measurement you can make with the device, because it establishes by applying these rules to a device, it establishes the uncertainty of the measurement. Okay, so that's the case of of a situation like that. Now, if I had another piece of wood that say was larger and actually went to someplace like here, let's say, right, then in this case, now I might not be able to determine. So it looks like this second measurement, I'll put them in purple and blue so we can distinguish between the two. So 10.40 for the purple piece of wood. For the blue piece of wood, it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So 10.8. Now again, the least count is the 8, is in the tenths of a centimeter's position, which in this case is 8/10 of a centimeter, 8 millimeters. And I might not be able to determine exactly where it lies in between the 10.8 and 10.9 digits, but I know it's not on exactly 10.8 or 10.9. And so there you just estimate. And in general, there's a couple of different things that people do. I just say, I just guess 0.5 or 0.05 for the estimated value. If it's not in between, doesn't matter, because you can't really determine, because, you know, like I said, you can't, that would be the next digit, the thousandths of a centimeter's position. And because of the rules that I gave you, you really can't determine what that is with this device. So I just, if it doesn't fall on a millimeter position, I just guess that the any guess you make is going to, at that thousandths of at that hundredths of a centimeter's position, is going to be just as inaccurate as any other number. So I just say 5. That's what I do. All right. So in that case, still the total number of significant digits is 4, with 1 being the most significant and 5/10 of a centimeter being the least significant. Let's put the units on there. So you can apply those rules to any instrument, you know, a scale, measuring scale. I mean, if it's not digital, a lot of times now all the devices are digital. Sometimes even the vernier calipers and the micrometers have little digital readouts on them. So they just, whatever the number is, they've already taken that into consideration and calculated for you. Generally in a face-to-face class, you know, the first lab that I would do is a measurement lab. And so we, you know, I go through you know, these rules, but also apply this to a vernier and a micrometer, just in the interest of time, and because a lot of times you have digital values. I'm not going to do that right now. I'm going to move on. But now that you know the rules, you could look these up anywhere, like on the YouTube or whatever, and they should go through, and you can apply and generally see that the rules that I've given you here are the basic rules that they're going to use and apply to a vernier or a micrometer, and give you the same, and be able to determine give you examples of being able to measure objects with those. I'm going to move on from here and just do one more thing before we go back on to Newton's laws, just because of interest of time, because it takes a little bit of time to go through and give those examples on that. But I hope that's helpful for you, and I hope that maybe refreshes your memory in case you haven't. For those of you who weren't that specific, and maybe there was something here that you didn't know, that hopefully that was worthwhile to go through that. But the last thing there is to take all of this now, and so now you understand how to determine significance. You've made measurements, right? But now you've got to make calculations. And this is, you know, I know a lot of you have been probably applying the rules that you know to the Wiley Plus, and this is the issue that we've been having, right? That doesn't matter what you do, it's going to get marked wrong. So again, just to say a word about that, you know, do your best, do the thing, don't waste time trying to get over numbers over and over again, just because most of you who we've taken have talked to me about that, we looked at specifically when we go in, and from my point of view, when I pull up the number, I can show you, we can see the answer. So, you know, I share my screen with you, and sure enough, it's the answer that you had. Sometimes they round it back, right, to something, but you had the answer. So just the protocol that I've been doing for the past couple semesters is just do the homework, turn it in, you know, submit it, get it graded. If you think there's a certain number of problems that have been marked too harshly, just send me an email with the numbers written so I don't have to guess. And then I just go back through and check it off and give you, you know, the majority of the credit back. Let's just do that. Emily, yes.
Hi, Professor. Good morning. I had a quick
Good morning.
question. Correct me if I'm wrong, but for the first measurement in blue, I think, would it be 10.60 rather than 10.40?
Oh, yeah, sorry.
Oh, okay.
Dyslexic moment. Yeah, sorry about that.
No, it's okay.
Wow. Yeah, 1, 2, 3, 4, 5, 6. Yeah, so sorry. Yeah. Thank you for pointing that out. Awesome. 1, 2, 3, 4, 5, 6, 7. Oh.
And so in that case, 0 is still an estimate, right? Like since it's so close to the actual millimeter line.
Yeah, yeah, yeah. The mistake is I just somehow saw 4 instead of 6, but the rules are all the same, still the same measurement. It's right on it. You can't really. It looks like it's falling on that position, so the estimated value would be 0 for that particular measurement. So absolutely, yes. Sorry about that. So anything else? Is that good? Yeah. All right. Last thing, let's throw it in here with operations. And also say a word about uncertainty. Maybe have a definition for it. And again, you know these, I'm sure, but let's just make sure we're on the same page. Operation and significant. Oh yes, let's do it this way. So for addition and subtraction, so I'm sorry, multiplication and division, the rule is determine, you determine the, yeah, that's, so for multiplication and division, let's say we can then, so determine, the significance is determined by the number with the fewest significant digits. So, for example, if I'm multiplying the numbers 5.21 times 0.032, I'm going to 5.21. So based on the rules we just determined, this guy has 3 significant digits. This guy has 2 significant digits, right? So it doesn't make sense that whenever I make a calculation, multiply these numbers, that is, that the answer is going to be more significant than the least significant number, right? That just doesn't make logical sense. So therefore, when you're multiplying and dividing, the least significant digit or value determines how significant that resulting operation, the result of that operation will be. So in this case, you're going to get something like 0. On your calculator, 0.166 and whatever else, so on and so forth. But you know that it can only be significant to 2 significant digits. So then you apply the rules of significant digits again, and you realize that this number can only be significant to this value here, right? So then you you truncate the number to that value, and then use what I'm sure you know is the basic rules for rounding off a number. So if I'm going to truncate and bring this back to the, I guess, thousandths of a whatever, the thousandths place, then I have to use the rules for rounding. And the general rules is what you've already been doing, I'm sure, is that since I'm truncating this number to the thousandths place, I look one digit beyond that. If that number is 5 or greater, then I round this number up to the next digit in the thousandths place. And if it were less than 5, then when I truncate to the thousandths, I just leave it as is. So in this case, I would report the final answer to be 0.017. Okay. Now, generally, we don't write numbers like this. We use something called scientific notation. Just because when you look at a number like this, you might have to think a little bit, right? Just even a slight amount of time, a slight, number of milliseconds. I don't know how we're, like, because it's just kind of cumbersome. You have, for me anyway, I have to think a little bit about the rules that I just mentioned. So scientific notation is a way of basically writing a number so that you kind of have to think less in terms of the significance. And the rule is that you have an argument, and the argument is the value that you're multiplying the base 10 by. So the way that I would write that is 1.7, and of course, when the decimal moves to the left, that the exponent on the base 10 because what is it, negative? Yeah. So then that's 1.7 times 10 to the negative 2. So this portion right here in parentheses is called the argument. In general, any number in a parentheses of a function is an argument, like cosine, or whatever the thing in the parentheses is the argument. And same thing for like log functions, whatever. But technically speaking, the argument is written to the number of significant digits that you should have. So like, yeah. So like this is not a good example, but if I had like, whatever, I just leave it at that, right? So you can see just on first glance, when I look at this, just the 2 significant digits clearly jumps out at me. It's almost I don't have to think. At least but when I look at something like this, I might have to think just a little bit just to make sure. And so if you have a bunch of numbers like that, written, obviously it's going to be easier to use scientific notation because it's just much more clear at first glance that the value of the significance of those numbers, and it kind of reinforces it, right? Like if you've taken the time to convert a number to scientific notation, then it just gives confidence that somebody, if it's done correctly, has thought about and specifically enforced the fact that this is the significance of whatever that number is representing. All right, and then finally, addition and subtraction. Oh, and by the way, again, going back to the Wiley Plus, I think I said this the other day, but Wiley Plus does not take this a number written this way in terms of scientific notation. It will always mark it wrong. So what you have to write is this number in scientific notation for Wiley Plus would look something like this: 1.7. You still go through technically, you should go through all the, the argument should still be written to the correct number of significant digits, but then without any spaces, you write a capital E and then the exponent, in this case, -2, without any spacing whatsoever. Now, again, because of the rounding off, sometimes it still gives you issues with that taking off, something. But if you don't write it like this, even if it's right, it won't give you any credit whatsoever. Like if you write this, it won't even give you partial credit. It'll mark the whole thing wrong. So this is how you have to write scientific notation for Wiley plus. Okay. And finally, then addition and subtraction. The significance is determined by, what I have written here is the number with the least uncertainty, i.e. the fewest digits to the right of the decimal point. So I guess I said that a little bit different just to emphasize the idea of uncertainty. I could have used that terminology here as well, right? And again, it's the same logic that if you think about it, that is essentially what is being determined here with these operations, with like I said that based on the rules that we had, this guy has 3 significant digits, this has, 2 significant and 3 significant. So if this were a measurement, for example, from a meter stick, then, well, I guess we won't say that because it would have to be like a more precise value. I don't know. Yeah, we don't know where the numbers come from. I won't say that. But yeah, whatever. I'm going to move on to this example. So determined by the number with the least uncertainty. And I guess I'm determining uncertainty by the number of digits. Yeah, the fewest number of digits to the right of the decimal. And sometimes it doesn't have a decimal, but still in the case, I guess the fewest number of digits. Yeah, I don't know. I guess we're gonna, yeah. I've never known any way to say this comprehensively. What language to use? I don't know. I've never been able to figure it out. So, because sometimes obviously you can write numbers without a decimal, and in that case, I guess you would say it's the numbers that I don't know what language to use. It's just easier to give examples. But generally, because we do have decimals when we write the values, at least I can, if the values do have decimals, then you can say this. But once I give the illustration with decimals, I think you'll see what I mean, how you can apply it to a number that's not written with decimals. Anyway, fewest number of digits to the right. Decimal. Oh, I guess I just thought about it. If there is no decimals, then it's going to be the number with the fewest non-zero digits Yeah. If there is no decimal, then it's the number with the fewest non-zero digits, period. Yeah, I think that works. So fewest number of digits to the right of the decimal, or let's write this like this. So these are points, subpoints above below this. Fewest number of decimals to the right, or in case of no decimals, it is the, what did I say? The value with the fewest non-zero digits. So that would be how you would practically determine the 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 number with the highest uncertainty. If there are decimal points, it's the number with the fewest decimal. Sorry, if there are decimal points, it's the number with the fewest number of digits to the right of the decimal. If none of the numbers have decimal points, then it's the number with the fewest non-zero digits. It's going to be the least certain, or yeah. And I think I have a double negative here. It's determined by the number with the least certain amount, or the highest uncertainty. Highest uncertainty, right? I don't know why this always just trips me up. I think it's just hitting my whatever. Uh, determined by the number with the yeah. I said yeah, that was a typo. I said least, but it's actually largest. Yes, sorry, because there's a it's the uncertainty is a word that's written in the negative, so it's like having a double negative means the opposite of the thing that it implies. So my bad. So it should be largest uncertainty or highest uncertainty. Yeah, the highest uncertainty. All right. So yeah. And if you're writing, so basically you probably already know how to do this, but I just want to make sure in terms of the definition of certainty or uncertainty, you know what it is and why you're doing it. So 35, if you add a number, 35.213, and you're adding that to, I don't know, so subtracting it, let's say minus, what do I do? Minus 29.1. So you're going to get something like, yeah. So on a calculator, would that be like 6.113 or something? Let's see. make sure. Yeah, 6.113. Or sorry, 6.113. So again, it's the same. This would be kind of contradict logic, right? Clearly, this number is the largest uncertainty. So this number is more certain than this number, because if I'm making a measurement and all the numbers are significant, I've taken this number out to the thousands, to the thousands of a decimal place. And this number, 29.1, is only correct or certain to the tenths of a decimal place. So this guy is a more accurate or more significant and more certain value in terms of measurement than this guy. So it doesn't make sense that if I'm making manipulation and calculating numbers, it doesn't make sense that the result should be more significant than a number that had a smaller significance, or should be more certain. I'll use that term, because more certain than a value that I use to calculate that number. So that's how this number that is more uncertain is determining the certainty of the resulting value. And so in this case, it's determined by not the total number of significance, because this has 3 significant digits, but it's determined by the most, or the least certain value, which in this case is in the 10th place for 29.1. So that's why when you're adding numbers, the resulting number can only be significant to, or certain to the 10th place. And therefore that would dictate the number of significant digits in that value. So, and the rule then when you're adding and subtracting is just whatever the least certain number is, that becomes the, you truncate all the numbers, in this case, to the right of that value, whether it's a decimal or not. And so, and of course, you still, actually, there is no rounding, right? Because, right, there's no rounding when you are, or yeah, it's the estimated value. So you do round. So you truncate and you round there. In this case, since it was below 5, the number in the 10th place, then below the value 5, when I truncate, then I just leave the number in the 10th place, in this case 1, as it is. And so this is the value that I would report as the final answer for this operation. And then the resulting answer would only have 2 significant digits, the number in the 10th place being the most, being the estimated value and determining the certainty of that final result. And finally, after saying all that, for orders of operation, I've been saying this quite a bit when we've been doing our calculations. When you're rounding a number, you don't do it to the very end, right? So let's say that I had a bunch, whatever numbers, and I'm doing calculations. If I now use this number here, and then and really it's kind of more implied for multiplication and division, but anything, it doesn't matter. If I round off every time that I get a result, then in the end, I'm introducing round off error into my final result. So the thing is that you want to get accustomed to storing all values in your stored registers as you make calculations. And then when you're reporting the final answer to the correct number of significant digits, you reduce the amount of round off error that can be truncated in, that can be translated through your operation, your mathematical operations and calculations. Oh, okay. Record keeping is over. Let's get back to physics. Well, I hope you didn't find that a waste of time. I'm sure most of what I have said here, you probably already knew, but there might have been one or two things here or there that you didn't, or that you just needed to be reinforced so that it's not challenging your confidence. And again, this is an introductory course here, this of all the three. So of all the courses, this is the place where those little details should at least be addressed. And so even though it takes time, and I just feel like over the years, for all for several reasons, it's just my experience to go ahead and do it, and at least once. All right. Any questions, problems, troubles, and or gripes? And also, I promised you that I would be comprehensive, so as comprehensive as possible. So I'd like to honor my word. I need to take a quick break, 2 minutes. I know we're not at 9:30 yet, but I need to take about 5. What we're going to do next is introduce Newton's laws, Newton's laws of motion. And again, many of you probably know various versions of these. When I come back, I'm just gonna maybe just have a little dedication, if you will, homage to Newton. I like to do that because it's just so significant and the foundation of basically the modern era. So you might maybe take a note too. I don't. Sometimes I put these little exposés in the module. I don't think I did that for this. They're here, but just take a minute to either Google the laws. If you don't know them, you probably do. Just review them real quick while I'm doing the break, and then we'll come back and we'll say a word or two about them, and then we'll go into the laws and start to introduce them, and all three laws, kind of as a quick review overview, and then we'll go into each of the individual visual laws and look at them quantitatively. So give me about maybe 7 minutes. Thanks.